right, let's give it a whirl. So today we're going to be talking about a section in chapter 4. I think it's 4.2, 4.3, and 0.4. So we'll probably finish most of chapter 4. There's a little bit at the end that I probably won't bother covering. So Kathy, my hope is today what we're going to do is we'll go ahead. I'll probably lecture for about an hour, and then we'll do like a little lab thing. So we're not going to be here for about more than 2 hours. That's my guess. So, all right. So to begin, we'll look at this information hiding and encapsulation stuff, and we'll talk about that concept and what that means. And this is actually kind of an old practice in software design. Goes back about 30 years, and the words don't really mean anything yet, but they will eventually. So what we're trying to do here is we're trying to encapsulate or limit or prescribe kind of where we or how we access data. And so one of the ways we do that in Java and a lot of other languages is we're going to name some aspects of our code and of our classes. We're going to call them, we're going to name them to be private. So far we've seen a lot of code where we had the word public in, and so we said public, for example, public class, whatever you want to do. Right? And so we've seen this. And when we define in our classes, when we went ahead and created a class, we would have a statement like public int, I don't know, name or something like that, whatever. And so here's this word public again. And so this is the way that we could declare instance variables in a class. And I kind of intimated as we went through this the last couple of lectures that we wouldn't always be having these things be public, and this is kind of where we'll see that we don't have them be public. In fact, oddly enough, for most instance variables we have in classes, we never describe them to be public. We always make them private. So we'll change this keyword here from public to private. All right? And so the question is, well, what does that do? And then B, why do we do that? So what private means in Java is that only methods of this class, that is of the foo class, only the methods that you define in this class can actually access this variable. So for example, I could have, let's make this method public. I'll talk about private methods later. Now let's make it void. And let's say this is like change name or something like that. So we'll do that. So in this method, because this is a method in this class, and this variable is private, so it's private in this class, I can access that if I want to. And so for example, I could say name, I don't know, gets 3 or something like that. Something silly like that. All right? Okay, so having done that, how would you go ahead and use this method? Well, the first thing you do is you have to make a method, you have to make an object of our class, an instance of the class. We do that in our normal way. So I could say something like, I'd have some other code elsewhere. And let's make this code in a different class. So let's put this in, should squoze this over a little bit more. Let's put it up a new class up here. So I'll call this public class foo driver. And in here I'll just have a main, public static void main, and the usual arguments over there. Won't bother writing them out. And in here I'll go ahead and I'll make a new foo object. So let's say foo f equals new foo, like that. So we've seen this many times before. So in here, I can go ahead and I can say f dot change name. All right, and that will invoke this method over here. Right, and so what you can, again, if we just sort of stick with our graphology we were using before, we would have like f is this variable, and f is pointing to an object. In this case, the object only has one field. It's called name. And so when I call this method here, that's basically going to write a 3 into the name field of that object. All right? So far, nothing new. So here comes the new thing. What I cannot do is I cannot say f.name gets 5. Right? That does not work. It will not compile at this point. Right? So how come? Right? Because I have one of these foo objects, and I know a foo object has a name field, so why can't I access the name field and put 5 into it? And so that's what this private did over here. So I can't access name here because this method, main, belongs to the class foo driver, not to the class foo. Right? So the only way you can access private fields is if you're in a method of the same class. That's the only way. Right? So that's what happens. The question is, why do we want it to happen? And that's where this terminology about information hiding and encapsulation comes into play. So, and as the slide says up there, it says, well, information hiding is what we're trying to do is you're trying to separate the implementation of a class from basically how it's used. So we want people to be able to use our code to do useful work, but we don't want to require of them that they understand how our code does what it's supposed to do. And so that's where the information hiding comes along. We're hiding sort of the underlying low-level nitty-gritty details of how our code does its work. We want to show up on top, want to make public to everybody our class, or classes, so they can go ahead and make use of those classes if they want to. So that's kind of what the term means. So information hiding is what we're trying to do, and the way that we do information hiding is by doing encapsulation. And encapsulation means that we're going to combine all the data of a class and the methods of the class are going to be encapsulated in basically this construct that we're going to use in these public and private things for. All right. All right. So there are some acronyms related to the concepts of encapsulation and information hiding. These are API, which stands for Application Programming Interface, and ADT, which is Abstract Data Type. And they're actually fairly similar concepts. There's slight differences, but it's fairly subtle. And you may have heard the term API before. I think I may have thrown that term out there a couple of times. But the idea behind an application programming interface is this is kind of the public face of the application of your program. And it says, well, here is, if you want to use my code, you only need to know about these things that are listed as part of the application programming interface. When we never say it all, we just say APIs, listed as part of the API. And so you only need to know the names of those methods, right? You need to know like what kind of parameters they take, and that's pretty much it. And of course, then you need a description about what the different methods are going to do. But you don't need to actually see the code itself. So for example, when you call, when you're working with string objects, and you have a string s, and you call s dot to lowercase, like that, you don't need to see the code that implements the to lowercase method. Somebody else already wrote that code. All you care about is that it doesn't take any parameters, and I know that this returns the same stuff that was in S, but all the uppercase letters will have been converted to lowercase letters, and all the other characters will be left unchanged. So usually write like something like that. So I want to change S so it's only lowercase. So that's what we mean by an API. You basically, you go on to the web, you can look up the API for the string class. The string class will list all the methods of the string class and what they do. So the kinds of parameters they take, what those methods do, and that's all you need. You don't care about the actual underlying code, which, you know, there's a lot of it, thousands of lines of code to implement most of the classes in Java, but you just don't need to know about them. So that's what I mean by an API. I'll try to just pull up a quick example here. If I bring up a browser window here, and let me shrink this so it'll fit in the screen. Fit here and there. All right. So whenever you want to kind of look up methods in Java, you can just type, I want to know Java, and I want to know to lowercase, and you'll get different things will show up. But if you look for, here it is, this one here. So if you look for the documentation online from Oracle, Oracle basically owns Java, you'll pull up a web page that describes the class string, and it'll talk about kind of what a string is and how you create strings, and then you'll get field summaries. That's the class variables, the instance variables, and then you'll get a list of constructors, which we're going to talk about in a little bit, and then a list of all these different methods like char at and code point before. So this is all these methods here. So this is the API. Right? This is the application programmer interface. So it just describes these are the sort of the outward-looking aspects of the class, the public elements of the class that users of the class can take advantage of if they want. But you don't see the underlying Java code that actually implements these things. Okay, so a related concept to API is ADT, or abstract data type. And this is actually, to some extent, an older concept than the API. ADTs go all the way back to the 70s, maybe even the 60s. And the idea here, the concept of ADT preceded object-oriented programming. And so before we had object-oriented programming, we actually used ADTs to help design large code systems that we're putting together. With the advent of object-oriented programming, ADTs kind of you just get them for free now because they're just built into object-oriented programming, the concept of classes and methods of classes. That's just ADT written large. So ADT, abstract data type, usually, you could just write this down real quick here. If I wanted to do an ADT, very similar to an API. Again, with an ADT, and the A is the abstract, that's kind of the important part, that's the abstraction. So again, I could talk about a string as an abstract data type. And I could say, well, there's a string and it encodes this kind of information, right? It stores this collection of characters, and it has these particular things you can do with the string. Like I can call to lowercase, and I can call char at, or whatever. The methods take these parameters, etc., etc., etc. So it's abstract in the sense that I don't know what's going on at the low-level details. It's kind of at a higher level of abstraction, so I only need to pay attention to the names of those methods and what they do, how they work. I don't need to know the low-level stuff. So very similar concepts. Okay, so I've already kind of told you basically how the public and private modifiers work. So when something is declared as public, that means that there's no restrictions on where the instance variables can be used. They can be called, as long as you have an instance of the class, you can access all the public stuff of that class. So public methods, you can call them anywhere you want. So in my example over here, when I had my food driver class, I could call change name because I declared change name to be public. Meaning I can call it anywhere in my code I want to, whether I'm in a method that's in the food driver class or in the food class, it doesn't matter. So same thing was true for my instance variables. So if I, again, just put this up briefly, if I had public class foo, one more time here, and I declared this to be public, and I called it F, so public int F, like that. So as long as this instance variable is public, now this is okay, and will work just fine. And that's basically kind of the code we've been looking at last week, which is why we declared them all to be public, because we didn't want to mess around with the whole encapsulation stuff yet. So now this would be legal, because I have an object of the class, of the foo class, and so I can access all the public stuff of that class. And now f is public, so I could access it. But we're always going to be making our instance variables private. And so you might say, well, why? Because it just seems like it makes life more complicated. Once I make this private, then this line this won't compile anymore. So why do I want to do that? What I'm doing when I'm declaring this to be private is, in a sense, I'm hiding f from the rest of the world. Why? So the why is, that's where encapsulation comes into play. I want to be free as the programmer, the designer of the foo class, to change the underlying low-level stuff if I want to. And maybe it's because, I don't know, the hardware changed and I can make it run faster, or I just want to update something. Usually it's to increase performance or security or something like that. And I can change all the private stuff in this class however I want. And because it's private, no other class out here knows about the private stuff anyways, so they don't depend on the code. So I can update stuff over here if I need to. And the only thing I have to be consistent about is everything that's declared public. And that's the API, the Application Programmer Interface again. So just switch back to that. So this is the documentation for the string class. And I could change, as you know, the folks who work at Oracle, I could change the underlying code that implements string, no problem, right? Just so long as, and make that text a little bit bigger, it's tiny text. There we go. All right. So as long as these methods, like compare to ignore case, as long as it does these, it still does the same thing. It compares to string lexicographically, ignoring case differences. As long as it has the same behavior, and I get more detail about it if I click on this, it'll tell me a lot more detail about what it does, right? As long as it maintains that behavior, I can change the underlying code in whatever way I want. And so that basically allows, for example, two people, one person to be working on the foo class or the string class, and one person to be writing code that uses the string class or the foo class, and they don't need to really, they won't step on each other's toes. As long as these methods keep working the same way I said they would work for, like it's stated in the API or if it's stated in my abstract data type declarations, then are okay. And that allows basically different groups of people to be working simultaneously on large pieces of code. And so that's pretty much why we do this. All right, so this then kind of shows what we typically do. So it's considered good programming practice to make all instance variables private. And in fact, that'll kind of be a requirement for this course. From now on, all of our instance variables are going to be private. You almost never want an instance variable to be public. Most of the methods in the class, most, definitely not all, we will declare to be public. So that's when I first put the foo method, foo class up here. I had a public void change name up here that did whatever it was going to do. And so this is public. And usually your methods are going to be public, with an important exception. And the exception is going to be when we have helper methods. So what do I mean by a helper or a helping method? It is often the case that when you're writing one of these public methods, you're going to want to call a method or some other methods whose only purpose is to help complete the work that your public method is trying to do. And so those methods that are kind of helping this sort of bigger, more important method do what it needs to do, those are called helper or helping methods. So you might have, for example, I'm just making something up right now, but you might have, do some calculations like int x equals, I don't know, x times 3, whatever. That's not going to work. Fine. Let's do x equals 33 times 15 or whatever, and then I could call some other method. So something like change. And I'll pass in x as a parameter. It's like that. You would never do this, but just as an example. And so here, when I'm calling change, I might very well have this be private, void, change, takes an integer parameter, and all it does is it takes the private variable f and it assigns it to whatever the argument is passed in, something like that. So in this case, this method change here only exists to let change name do its job. And because of that, I make this private. So that this method is private means, again, go over here to the foo driver class. I can't call change. Right? If I try to do that, this f.change 42, right, that won't compile. Because again, the change method is private. So I can't call it. In fact, you wouldn't even really know that it exists, because when you go and read the documentation, if you read the API documentation for the class, it won't even mention the private methods, because you can't call them anyways. So they won't be listed. So we don't bother to do anything with the we don't list the private stuff. It doesn't matter. Okay. So next is these funny terms, accessor and mutator methods. So we've decided we want our instance variables to be private. Why do we decide that? We decided again because the low-level details about how the class is implemented should be hidden from the users of our class. They don't need to know. But once we've declared these things to be private, then it might be that we still want the users of our class to have access to that private data. Right? And that's where the accessors and mutators come into play. It seems kind of silly because first we're going to make them private and then we're going to provide public access to them anyways. But again, there's very good software engineering reasons for doing that. So, let's erase this here. All right, so I've got my class, I've got a private instance variable. If I want folks to have access, the users of my class to have access to the instance information, I can do that through the use of accessors and mutators. So accessors look like this. They're going to be public. This data type is int, so this method is going to be an int method. And I'm just going to call it getF. Like that. And then this is a real simple method. It only has one line of code. It says return F. Like that. Right? So this is an accessor method. So now over here, change up my code a little bit. There's some other lines there, I don't know what it's doing, but later on I decide I would like to be able to, and I'm going to change this. Yeah, that's fine. Let's actually give this thing a name because all the F's are going to get confusing. Let's call this Sue. All right, so I have Sue as a foo, so I made a new foo object. So now over here, what I might want to do is something like int m gets Sue dot get F. Like that. All right? Remember again, if I tried to just say m gets Sue.f, like that, that won't compile. Because F is private. The main, this particular method, main, is a method of the foo driver class, not of the foo class. So I can't call that. So that won't work. But this will work. Because now I'm calling getF, and getF is a public method of the foo class, so anybody can call it, including methods of the foo driver class. So now I can call this method, and it basically does the same thing. I'm going to be able to get the value of the F field, I'm going to return it, and I can store it in a variable and do whatever I want. So that is an accessor. right? Because you're accessing the value of one of the instance variables. So the next term is mutator. The mutator is, mutate's just basically the Greek-based word for changing something. And so now I might want to write code where I want to change the value of f. So again, I can't do this. I can't say su.f gets some new value like 42. That won't work because again, f is a private variable, a private instance variable, so I can't have access to it. So what I'll do is I will create a public method this time. I'm going to make it void for now. We'll fix that in a minute. And I'll call this setf. And it's going to take an integer. And let me make this g for now. And all this will do is it'll say f gets g. All right, so now I can, that won't work, but this will. So I'll say su setf 42. That. Now I'm good to go. Because su is calling this method called setf, which is public, so anybody can access it. So I'm going to call that method with the argument of 42. So 42 is going to get mapped into the g parameter over here. And I'm going to take the value of the g parameter, 42, and I'm going to store it into f, the private field of this object. All right? So that is a mutator. Right, now the words accessor and mutator have lots of syllables. They're kind of clunky, right? So what we use, what most programmers would call these, is we'll call these getters, and these are going to be setters. So that's more common terminology. All right? And by convention, the names of the getters and setters always have this form: the word get, and then the name of the field. You could go ahead and capitalize it if you wanted to, just to stay with the naming conventions, which is what I did here. So just to indicate word boundaries, I would have said get and make this a capital F, even though the name of the instance variable is a lowercase f. Right? Same thing over here. The names of the mutators are always set, set, followed by the name of the instance variable. Again, follow the normal capitalization stuff. And then you're going to take a parameter, which is the same type as your instance variable's type, so you can map them in directly. So that's getters and setters. And the interesting thing is that because this programming practice, encapsulation, and having all of your instance variables be private, and you're having your accessors and your mutators being public, most professional level IDEs, like Eclipse, for example, not BlueJ unfortunately, but Eclipse, they will automatically create getters and setters for you. Basically, you'll just click on a button, it'll look at the declarations of all your private fields, and just whoop, make a get and a set for each one of them, and there you go. Automatic code. Happy, happy. Less work for us. Okay. So here's a nice little picture from your textbook, which kind of talks about how encapsulation works, sort of pictographically. And so the idea here is that we've got the sort of purple circle over here represents a class or a set of classes. For now, just a single class. And so the idea about this, the purple exterior here is that you can't get in that way. You can only get into the code through the public interface. So this little orange box here represents the public methods and the public instance variables, of which there won't be any, but you could. That's the only access you have from the outside world. Right? Then this orange circle in here, that's the implementation of the class. That includes everything. So the private instance variables, the private constants, the private methods, and all the public stuff's here too. It's all accessible. But you can think of the public stuff kind of is both sides. It's accessible from the inside and it's accessible from the outside. And so here we've got a user of our class or our classes, and they have access to the interior stuff only through our public interface. That's the only way in. Okay. one kind of subtlety is that I was very particular about the way I was describing how private access works. So what I said was, once something's declared private, you can only access the private stuff within a method of that class. Importantly, right, it doesn't matter how you got to that method in the class. It could be called from another object, and that would be fine. So, as an example, let me modify this just a little bit, and let's have blah, blah, blah. Let's make a new method here. I'll just erase this so I save a little screen space. All right, so I've still got my foo class. That's fine. All right. So what I can do is, let's do it this way. Yeah, move this over here. So here's foo again. Public class foo. And I got my private instance variable still. Private int f as before. And let's have, let's do it this way. Let's call it public set to, let's call it something else. Let's call it modify. And in particular, this is actually going to take a parameter, which is another foo object. So, and what I'll do is I'll say f gets other f, like that. And then let's see how we could actually call this. So let's do this, blah, blah, blah. Let's make a foo object over here as before. We called it Sue. And I'll say Sue dot set f. I'll assume I still have those mutators over there, the setters. Sue dot set f. Let's make it 5. And then I'll make another foo object, Bob. This new foo, like so. And then I will say Sue. Bob dot set f 10, and then I can call modify. Let me do this one. I'll say Bob dot modify Sue, like that. Okay, and pictographically, right, what we have is I've got Sue pointing to an object, and when I say it's set f, that's going to set f over here to be equal to 5, and then I make Bob. Bob points to another instance of my foo class, and this line over here sets f to be equal to 10, like that, and then I call modify on Bob. So here's Bob. Bob calls this code up here. Right? So in the context of this invocation, when I say f here, I'm referring to this f down here, right? Bob's f. Right? Then we have other up here. What's other? Well, other is Sue, when I called that here. So we kind of have two variables. Here's other. Both Sue and other are referring to the same object. That's this object here. Right? And I could have made this explicit if I wanted to. Right? We talked about this last time in terms of every method has an implicit parameter called this. So I could have written it like this. This dot f gets other dot f. Right? So whenever you call a method, this is always bound to the calling object. In this case, the object that made the call was Bob. So we also have a variable called this, which is implicit. And that's pointed to the same object up here. So what this does then is it takes the value of the f field of other, here, 5, and it stores it in the f field of this, which is here. So that's going to change this. It'll copy this 5 and put it down here instead, and you'll do that. All right, now, the whole purpose of the example was to demonstrate that I can access f for other even though f is private and belongs to this other object. But that's okay, and that's basically what that whole slide is trying to say. This is just saying, once you're in the method of a class, you can access all the private stuff of all the objects of that class. So in this case, other is another object. It's not the calling object, which is Bob. But that's okay, because they're both in the same class, so I have access to all the private stuff of the class once I'm in the method. All right. All right, and I said I would fix this. I kind of talked about it before, and then here I'm getting kind of explain what I wanted to do in the end. Normally, when we're defining getters, or sorry, when we're defining setters or mutators, often rather than declaring the setter to be void, we declare it to be Boolean, and we have the return value just indicate whether or not the value was successfully assigned to the instance variable. So true, I succeeded; false, I didn't succeed. And so this little sample piece of code I put down here kind of shows how you might do that. So I would call the setter, set name, I say bob.setName, pass a parameter, and I assume what this is going to do, it's going to change this instance variable in the object called name. It's going to set it to whatever the contents of this variable is. And as long as that works, it'll return true and everything will be happy. If it returns false, then I've got this not over here. And so if setName returns false, then the not flips it to be true, and then my if statement will succeed, and I'll actually then print out bad name or some kind of error message, something like that. So this is often a trick that we use, or a behavior that we use when we're designing our setters. So not a particularly good case here, but if I so put my setter in there again, let me close that off. So I could have public, and I'll change this now to be Boolean, and I'll say set f, and whatever I want to get. It takes an integer, call it g, and I could do something like if g is less than 100, then f gets g, and I will return true. Just making something up here. Else return false. So pretty common setup. So maybe it's the case that in my API someplace it says the f field can never be bigger than 100 or something like that. And so this is one way I might enforce that. If I try to call a method with a number that's too big or illegal in some way that I've described in my API documentation, then I will return false. I won't allow the value, the f field to take that name, that value, and I'll return false. But if it's a legal setting value, then I'll just make the assignment and I'll return true, and all is well. So a pretty common trick. Another thing we'll often see with setters, if we don't want to go Boolean, often what we do with setters is we just return the new value of the instance variable. So if I was taking that on, I would just rewrite this pretty simply as, you could do it in 2 steps. I could do this, so I could say f gets g and return f. And of course, now I have to change the return type from Boolean. It has to be int. Right? So I can write it that way. Or if you want to save a little bit of typing, you could write it this way. Return f gets g, and that'll work too. Right? And so what this will allow the caller of setf to do is to look at the value that's returned back and make sure it's the same as the one they passed in, which of course it will be in this case, but sometimes it's not so obvious. And so that's another kind of trick you can do. Of course, then you're going to change up the code that invokes this. You might want to say something like, do that. So now we would change this around, and it would be more like, make Bob, oh, sorry, erase that, I wanted, that's okay. So I could say, if Bob.setf10 does not equal 10, then there was some kind of an error condition and you want to do something about it. So you expect the return value to be the same as the one you put in, and that would be the case over here. All right, moving along. Okay, preconditions and postconditions. In general, when we're writing out the method, most of the methods that you write out, in your case, because I'm making you do it, all the methods you write out should have a little header comment on them that describes basically what the methods do. You wouldn't need to do it for something trivial like the getters and setters, because we know what those are supposed to do. You don't really need a method for those. You could if you wanted to, but you don't have to. So the precondition is just the programmer puts into the documentation, and usually into the API as well, defines what the method, or the programmer who wrote the code for the method, what the method assumes to be true when the method is called. The postcondition will state what will be true about the method or the object once the method returns. So the precondition has to be met in order for the method to work properly. The postcondition kind of describes what the expectation is of the behavior of the method. And in general, when you're designing a method, as the slide says here, it's good practice to think in terms of preconditions and postconditions, even if you're not kind of stating them very explicitly and formally. So I'll give you an example. And this is from your textbook. It's kind of small text, sorry about that. But basically what it says is that this is for the header comment for the toString method. And we talked about the toString methods last week. What we know is that a toString method is basically supposed to, when you invoke it, it's supposed to return a string which in some way represents the object, whatever it happens to be. And so you can see here's a statement of a precondition. It says the precondition is all instance variables of the calling object have values. Pretty straightforward. I need them to have values so I can generate the string that represents the object. Right? In this case, it doesn't really have an explicit postcondition because it doesn't make any, the toString method does not make any changes to an object. It just returns a string and leaves the object alone. So there's no real postcondition stated here, but there is a return. Say returns a string describing the data in the calling object. And that's, so again, this is, the header is described, the header comment is describing what the method is supposed to do. All right. Over here, for example, when I was writing, for example, the setf method, I could have written out a formal set of, sort of formal header here would be, take this format, I might say, well, the precondition, which I'll just do with PRE usually. So the precondition, well, there aren't really any preconditions here. There are not any needed, so none. And the postcondition will be, well, in the case, well, so the post, in fact, let's put back the case where I had the values had to be the right size. Now, Boolean, blah, 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 and I said, well, if G is greater than 100, then I'll return false. Right. Otherwise, I'll set F to be equal to the value, and I'll return true, like that. All right, so now the precondition up here, there isn't really a precondition because the precondition talks about the object that I'm calling setF on. Right? If I wanted, I could say the precondition assumes that G is less than or equal to 100. So I could write that. I could say G, or argument G, or parameter G is less than 100. All right? And the postcondition would be that F gets value of G and then returns true. All right, something like that. So this says, well, the precondition assumes that, and the postcondition tells you what's going to happen. It's a little fuzzy here because we actually, this method actually works just fine if you pass in a value which is bigger than 100. You just get false instead. So really, more accurately, I would write it this way. The postcondition is F gets value of G if G is, what did I say, less than or equal to 100, right? And returns true. True, right? Else returns false. And that would be your description of your postcondition. And then close off the comment like that. So that's the pre and post conditions mean. And so basically, this is in some sense sort of a helper, an aid to the programmer. When you're writing your code, you put a stipulate in the precondition what you expect to be true in order for your code to work properly. And then, inevitably, when your code fails, you go look at your statement and say, oh, I forgot the damn precondition. Yeah, I blew that. I wasn't making sure the precondition was being met before I called the method. All right. So, overloading. So, overloading describes the situation when we have two or more methods in a class that have the same name. And it's quite common. So, let me just show you an example piece of code. This is in one of the date classes. I think it's the 6th try date class. I can pull that up here. Move this into the middle of this screen that we're recording. All right, and you can see, so this is just another attempt at making a date class. Still has the same 3 instance variables we've been working with. You've got a string, which is the month, which is a string, the day and years, which are both ints. And here I have a set date method, right, which takes basically values that I want to put into these 3 fields over here. And this takes an int, an int, and an int. So that's a set date over there, and it sets the date appropriately. And I have another method down here with the same name called setDate, but this one takes a string and 2 integers. So instead of 3 integers, it takes a string and 2 integers. So they're 2 methods with the same name. They're both called setDate. They both do the same thing. They just do it in a slightly different. The code that implements the methodology is a little bit different, but they both do the same thing. They allow the caller to change the fields of a date object. In this case, a date 6th try object, but that's too hard to say, so I won't do that. So there's actually that one. Here's another one, setDate, which just takes a year. So you can call setDate, which is a single argument. And here you're basically going to say, you'll notice it's calling another setDate method here that has an int, and another int. So this method here, this setDate, is actually going to call this setDate up here. Int, int, int. So it'll call that one. So anyways, this gives you 3 different methods, all called setDate. So this is an example of overloading. So we have overloaded the method name setDate. So the critical thing when you're overloading is that the signatures of the methods, the overloaded methods, must be different. And what we mean by signature is the signature consists of the name of the method, in our example here, setDate, and the number of parameters and the types of the parameters. So down here in the text at the bottom of the slide are basically the signatures of, well, part of the signatures of these three methods of the date class. So they're all called setDate, but this one takes integer, integer, integer as its parameters. This one takes string, integer, integer, and this one just takes a single integer. So as long as these are different, as long as the parameter types are different, or the number of parameters are different, those are different signatures, and that's allowed. If the signatures are the same, then it won't compile. Java will say, you've already defined a method with that signature. You can't have two methods with the same signature. All right. And I should say the reason why Java cares, of course, is that when you invoke one of these methods, so in the code here, let's see, I can do this here. I think I'm okay for now. No doubt I'll have to put it back up in a minute. But in my class, in the example I had up here, if I had one of these date objects, a black pen, if I have a date object, date D equals new date, and some other code, whatever I'm doing here, and then I want to call this thing and say d.setDate 1492, like that. When the code compiles, the compiler needs to know which function am I calling, right, of the three methods that we just looked at in our slide over there. Right, which of these three setDates am I calling? Am I calling this one? Am I calling that one? Am I calling this other one? Which one am I calling? So Java will basically look at this and say, well, I only see one integer here. There's only one signature that looks like that in that code. And that's this guy here. It's called setDate. He takes an integer as a parameter, and so this must be the method that I'm going to invoke. So that's why the signatures have to be different, because Java needs to be able, the compiler needs to be able to tell which of those pieces of code am I going to invoke next. And that's why they have to be different. Okay, now one thing that can make this a little bit tricky is that Java can sometimes do automatic type conversion. And we've actually seen some examples like this before. And the idea here is that Java can convert some data types into more general data types when it wants. This has to do with the primitive data types that we talked about before. So in particular, a very common conversion is that ints can be converted automatically into doubles. So if I had created a setDate method, so in my class, if I had a date method, sorry, a setDate method, something like that, so in my date class, and I had public setDate, and I declare this to be a double, F or something like that. All right. And then with my date object up here, I say d.setDate 10. Like that. Well, 10 is an int. It's not a double. Java is very helpful. It says, okay, maybe you meant for it to be a double, because it's an integer, and I can easily convert that into a double for you. I'll just treat it as 10.0. And that is an automatic type conversion. So this method will actually end up, this invocation will actually call this method. And it will just convert the 10 to 10.0, and then it will call the method, and then it will run and do its thing, whatever you want. Which is usually what you want to have happen, but not always, right? So the last line on the slide there says, ambiguous method invocations will produce an error in Java. So this is fine so far, but there's some examples coming up. This would be a problem. Right? So here, if I had in my class two methods, right, both called increase, right? One takes a double and one takes an int. So on the face of it, the signatures are different. One takes an int and one takes a double. But the compiler will not allow this. And so Kathy, can you see why it wouldn't allow it?
So you put in int, you would know if you wanted to change that to a double or if you just wanted to...
Exactly right. So Kathy just said that if I called this now and I had both of those methods, both call them increase or something instead, d.increase or whatever it was, right? It wouldn't know whether I wanted to call the method that just had an integer as the parameter, or I wanted to automatically change the 10 to 10.0 and call the increase, which takes a double as its argument. And so it won't allow you to do both. Okay? One thing, which is a little unfortunate, but is done for good reason, is that the signature does not contain the return value type of a method. It only contains the name of the method and the number and types of the parameters. So you can't have two methods which are overloaded and differ just by their return value. And get that. So I can't, for example, have two definitions of set data, one of which returns a double and one of which returns an int, or one returns a Boolean and one returns a double. Well, it doesn't matter. I can't do that. And the reason why we can't do that is because you don't have to call a function as a function, basically. Typically when we call a function, that's a method that has a return value, and we usually want to do something with the return value, like store it in a variable. But we don't have to. So on the bottom line on the slide there basically says, compute this could be a function. It might do some fancy calculation and return the value of the calculation, and usually I would store that in a variable. But here I'm not. I'm just calling it, just like I would call a void function, a void method. I call it basically discard the value that is returned. So doing that, the compiler doesn't know what you're expecting the return type to be. So if I had two different compute this methods, one of which returns a string and one of which returns an int, just looking at that line of code, the compiler can't tell which one are you calling. If I had, something like string Bob gets compute this, whatever the arguments were, then there'd be a big hint to the compiler, right? Okay, he's expecting the return value to be a string, and so I should probably I'll call the version of compute this which returns a string instead of the one that returns an int. But that is not always the case, and so we basically disallow that. So you can't have two methods which are exactly the same signature but have different return types. That's not allowed, and that's why. All right, and this slide is mostly here in case you've had some experience working with other languages like C++ or C#. In Java, we cannot overload the operators. So like the plus operator for addition, we cannot overload that ourselves and say define plus to take some different arguments or minus or anything like that. So we can only overload methods that we can name. We can't overload operators. In some languages, you can. You can change the behavior of plus and minus. And really what you're doing is you're just making the plus and minus work with different data types. So for example, a common thing to do in C++ is if I wanted to have a library that allowed for vector manipulation. I might want to be able to add two vectors together. So I could actually define something that, a plus operator that took a vector over here and another vector over here and returned the sum of the two vectors as another vector. That's pretty handy to do because it makes the code obvious kind of what you're doing. You just use the plus, you just say something like v1 gets v2 plus v3, and these are all vector objects, and that works fine. It makes the code very easy to read, but we can't do that in Java, so turn your mind away from it. We can't do that in Java. You'll have to work in a different language if you want to be able to do that. But it's very handy. Okay. So I've actually kind of referred to this a couple times in passing. How do we go about initializing the instance variables in the classes that we are designing? So this is a very common way to do it. Basically, when you define the method, when you define your class up here, you'll stipulate when you're declaring the instance variable, you'll give it an initial value. So now when I do this, whenever I create a new mat object up here, it'll have a name field, right? And the value of that name field will be the string mat. Right? Nice, easy to do, code writes out real fine, no problemo. But of course, what this means now is whenever I make instances of the class, they'll all have the same name, which probably I don't want. Maybe I do, but probably not. Right? So, very handy, we use it a lot, but usually we want, the whole point about having multiple objects of a class, multiple instances of a class, is we want them to be different from each other. So the way, a better way for providing the initial values of our fields is through the use of constructors. So, and as you can probably tell from the name constructor, this is the thing that actually constructs the new object. Its job is basically to provide the values of the instance variables of the new object as we go ahead and create it. So let's look at that. And then I think we'll take a break after this. Okay, so a constructor is a special kind of method. In fact, some software engineers don't even call them methods, but a special kind of method that is designed to initialize the instance variable for an object. And they have a rather unique declaration for the methods. So here's an example right here. Right? And so you see, as before with any method, we have to either make it public or private. So we're going to make it public. There's no real reason to have, actually that's not quite true. There are sometimes reasons to have private constructors, but not very often. So we're going to make it public, and then the name of the method is exactly the same as the name of the class. So the name of a constructor is the same as the name of the class. That's how Java knows it's a constructor. You'll also notice that the definition of the method does not have a return type over here. Doesn't say void, doesn't say int, there's nothing there. It's just public, and then the name of the class. And then, like with any method, you have an open and closed parenthesis in case you have any parameters you want to provide to the constructor. And then the code that implements the constructor. And the last couple lines there on the slide say that constructors are typically overloaded. That is, typically we'll have more than one constructor for most of our classes. Usually at least one, sometimes two or three, but you're always going to have, almost always going to have a constructor. Okay, so a constructor will be invoked automatically whenever you use a new operator. So whenever you call new, right, you're going to be invoking a constructor. In fact, always a constructor will be invoked. Even if you don't provide one, Java usually will have a default that you'll be invoking implicitly. So here's this code that shows a little bit of an example. So I've got some class, whatever its name is. In this case, we'll just call the name of the class is class name. And so we're basically invoking the new method on the class, as before. and signs for providing arguments over. You've actually, of course, seen this before with, for example, scanners. Right? When we were trying to get input from users, we could say something like scanner, KBD for keyboard equals new scanner, and we had system.in, like that. Okay? So this is invoking a constructor of the scanner class. And it's providing this as the parameter, as the argument to the constructor for that class. So the way constructors work, and I've used this simile before, I've said, well, we've got when you call new, you're basically using the class as a cookie cutter. So you're going to cut out a piece of memory, which is the right shape, which is the shape determined by whatever the instance variables are for that class. So let me buff this up a little bit here, get rid of that stuff. So let's just add another instance variable for yucks. So a private string, let's call this name. That. Right. So when I call new, foo here, let's make 0 arguments for now, we'll fix that in a minute. So when new happens, Java basically takes this blueprint, this cookie cutter, and cuts out a chunk of memory, which is big enough to hold an integer and a string. Right? So it cuts out the chunk of memory, which has an int field and has a string field over here. And it's going to have this variable kbd is going to point to that chunk of memory. It refers to that chunk of memory. So what Java does, it first allocates the chunk of memory, and then it calls the constructor. And the constructor's job is to fill these in, to give those values, to initialize them. That's the main job of a constructor. All right? So, you can, inside the definition of the constructor, which we haven't quite got to yet, I'm going to show you some examples in a second. Inside the definition of the constructor, it's like any other method, it can call other methods if it wants to, in particular call helper methods and stuff like that to kind of do its job. A very common thing for constructors is actually to call other constructors, and I'll get to that and why the heck would you want to do that. I'll get to that in a minute. But it's very common to do this, and in fact the code that we're going to look at in the date class again does this all the time. So I'll get to that in a second. I want to show you some code now for how constructors work, so let's jump to that. And I think that's in the final date class. Yes, let me shift to that. There we go. All right, so this is the final date class in chapter 4. And here they've added some constructors. And so you can see we have our same instance of variables we've had through the whole chapter. You've got month, which is a string, and you've got 2 ints, day and year. And so here is the 0 argument constructor. I'm going to skip that one. Let's look at this one first here. So here's the constructor, right, which takes 3 ints, right, and it invokes setDate. So it's perfectly okay for a constructor to call other methods if it wants to. So in this case, it's going to call setDate. We actually already saw setDate on the previous version of the date class that we're working with. Remember, we had overloaded setDate, so there are 3 different setDate methods. So this is calling one that takes int, int, and int. And so that's this setDate down here. It takes this one and runs the code. And you can kind of see what it's doing. It's setting the month field of the object, the day field, and the year field of the object. So basically, first the cookie cutter cuts out a chunk of memory big enough to hold a date, and then this code is invoked and it initializes those fields. It assigns the month field, the day field, and the year field appropriately. Right? And then the method returns. So that's what it does. You'll notice there's no return statement here. It just sets the instance variables. That's all a constructor really needs to do, is to set the values of the instance variables. You'll notice that there are multiple constructors. Right? They are overloaded. So there's a constructor that takes no arguments, a constructor that takes 3 ints, a constructor that takes a string and 2 ints, a constructor that takes an int. I think that's, and one more, a constructor that takes another a constructor that takes an object of the same class as the new one I'm creating, and I'll talk about that later on. That's called a copy constructor. So there's actually 5 different constructors defined for this class, but they all are supposed to do the same thing. We're going to assign a value to each of the 3 fields of a date object: the month, the day, and the year. All right, and I just kind of showed you this, but I'll talk about it again. So like in any method, every constructor has a this parameter, an implicit parameter. You don't have to use it, but you can if you want. And the point here is that the this object, the this parameter, is always going to be pointing to that new shiny chunk of memory that we just allocated when we called new. So that's what this is going to refer to. So I can use this in my constructors when I want. It's actually quite common. So let me show you. Let's say, yeah, this is a good example right here. Let me rewrite this code. So you'll notice that this takes a month, a day, and a year, right? And so what I could do, for example, here, set date year, I could change this to, so instead of calling set date, I'll do it this way. Month, I could say like this, dot month, or I could do this. Let me make it, I'd probably write it like this. Month equals January. That, and I could say day equals 1, and then I could say this dot year equals year. I talked about this last week. This is one of the common uses of the this parameter, right? Because there's already an instance variable called year, but I have a parameter with the exact same name. So I can't write this because it wouldn't be clear to the compiler which year am I talking about. And am I talking about the parameter year, or am I talking about the instance variable named year? So when I put the keyword this there, that makes it clear. Right? This is the object that this method was called on. The brand new memory I've allocated, and I'm taking the value of the parameter year and I'm putting that into the instance variable with the same name. So that's a quite common use of the this in a constructor. So let's take a break because we've been going on for a while here, and